Hi there. Today we are going to talk about chemical properties, chemical changes, and we're going to wrap everything up talking about separation techniques. So in the last video we talked about density in more detail and how to use the formula and how to use table S in these density questions. So again today we're going to cover chemical properties and chemical changes. They're basically the exact opposite of physical changes. And then we're going to talk about how both of those physical and chemical changes relate and how we can use those to separate different forms of mixtures. So first, chemical properties. A chemical property describes the ability of a substance to undergo changes in composition or chemical makeup. So what that means is that, or when we're looking at these chemical properties, in order to look at them, a new substance is produced. So some of these properties include reactivity, toxicity, pH, flammability, oxidation. So like, for example, if we're going to look to see if something is flammable, well, if you're going to set it on fire, and if it sets on fire, well, it's flammable, but you also made something new. And so we're going to go into more detail about that and reactivity. Oxidation and pH is something we'll see later on. We have a whole unit dedicated to pH and a whole unit dedicated to oxidation. Okay, so flammability is a material's ability to burn in the presence of oxygen. So without oxygen, you're not gonna start a fire. I think if you ever, had a candle and you kind of covered it with a spoon or something, the fire will go out. It needs that oxygen. Now, if you're burning something to see if it is flammable, well, once you burn it, you're creating a new substance. During, fires, combustion reactions happen, and you're forming carbon dioxide and water vapor and other byproducts. So if you're forming new things, that is the definition really of a chemical change. Let's just go back in combustion reactions. So RXN is an abbreviation of reaction. You make carbon dioxide, you make water vapor, and other byproducts. So again, if you're making new things, that is a definition of a chemical change. Reactivity refers to how readily a substance combines chemically with other substances. And so right now, here is a little piece of lithium, here's a little piece of sodium, and here somewhere, just call it there, is a little piece of potassium metal. So these different metals are highly reactive with water, and the only way to test that is if you throw it into water and you can literally watch it explode. So this is what I was talking about the other day when I said if you put sodium in water, it explodes. So here is a tiny, 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 tiny piece of sodium, and there is that little fire. And then when, the sodium or the lithium or the potassium break down, you're forming different compounds, you're forming these different types of gases. So that is a chemical change. So again, chemical changes is when you're producing a new substance. So a chemical reaction occurs. So in the physical change, we took the word stampede and we changed the font. It was still the word stampedes. But now, if a chemical reaction is happening, we're going to take apart those letters, take them apart, and rearrange them in a different way to form two brand new words. So a new substance is made. Made steps is no longer stampedes. If we're looking at eggs, we're taking this, cracked egg and turning it into scrambled eggs. The chemical properties of the wet egg and the scrambled egg are now completely different. If you have a bike, if someone tells you not to leave your bike out in the rain, it will rust. All this rust, this orange stuff, is a new chemical that had formed when water and other things had reacted with the metal in the gears. So again, in a chemical change, your identity of a substance is changed. A new substance is formed. So a few examples are rot, rust, burn, decompose, corrode, oxidize, ferment, explode. So if you see those words, those are kind of key words for chemical changes. So this GIF, as you wait for it to reset, is a picture of sugar cubes. And the thing that's being poured on top of it is sulfuric acid. So when the sulfuric acid interacts with the sugar cubes, like this, it's literally decomposing and changing the chemical structure of the glucose. So now everything that you see, there's different steam that comes off of it that's releasing different forms of gas. But the stuff that's left behind, all that black, is just that carbon that was in the sugar. So when we talk about burning things, so like the burnt cookie example from the physical change video, that that's just what that's what happening to the cookie on that molecular level. You're changing the chemical composition and leaving behind only different things. And again, some evidence of a chemical change: if it changes in color, if it changes in odor, so now it smells different, you've produced a gas, you've produced a precipitate. So a precipitate is like a solid in that form. So if you mix, here's chemical A and there's chemical B coming in, and it forms, some stuff on the bottom, that would be your precipitate. Or if it changes in light, so if it like decides, start glowing, if it, heats up, if it cools down, all those things are evidence of a chemical change. So again, some examples. I know this picture is kind of blurry, but iron rusting, burning wood, metabolism, cooking an egg, baking a cake, a battery, fireworks, oxidizing stuff, a rotting banana, and electroplating. All these things, you're changing the chemical constitution of whatever you are using. So again, this is the same slide as the physical change video and some helpful hints. So if you are looking at an example and you're not sure, ask yourself, well, did you make something new? And if the answer is yes, for sure, I made something new, I can see it, I didn't have this there before, it's a chemical change. If the answer is no, you didn't make anything new, well, that's a physical change. Like if you cut a piece of paper, it's still paper. If you're not sure, ask yourself question 2. So if you were to dissolve salt into water, and now you don't really see the salt anymore, and you're not sure if you know, made a new substance, or if you burnt a cookie and you're not sure, then ask yourself question 2. Can you undo what you just did? Can you go backwards? So in the case of the salt and water, you can get that salt back out of the water. If you just let the water sit, the water will evaporate and the salt will be left there on the bottom of the cup. So that would be a physical change. Though if you have the burnt cookie example, you can't unburn a cookie, and it's just like with sulfuric acid and the sugar GIF. The chemical makeup of that cookie is now completely changed, leaving behind that charred, left behind carbon in that burnt section of it. So here's a good way to kind of compare the two. In a chemical reaction, chemical change, before we had a wood log. During the change, the log is getting burnt, and when you're done with it, you're left with a pile of ash. You did not start with a pile of ash, you started with a log of wood. So if you're ending with something different, that is a chemical change. You have that new substance. Now, if we're looking at physical changes, and let's look at this lemon. If, we're putting it through the change machine and it's getting sliced, it's still a lemon getting sliced, but after, it's still a lemon. It's just a smaller piece of a lemon. You didn't make anything new. It is still a lemon. Okay, so is this an example of a chemical change? Burning wood. You should say yes. Because again, whenever you set something on fire and something gets burned, the chemical composition is being changed. That is a chemical reaction, a chemical change. Crumpling paper. Is this an example of a chemical change? The answer is no. Because it's still paper. You can uncrumple that paper. It's still paper. Nothing about that is changing. It now just looks a little bit messy. Still paper. Next, if we bake a cake, is baking a cake an example of a chemical change? You should say yes. Because if you're not sure, well, I had cake batter, now I have cake. Is that the same? And if you're not sure, ask yourself that second question: can you unbake a cake? And the answer is no. There's a lot going on when the cake is being baked, and at certain temperatures, different molecules will change shapes and denature and become different things. Like all the little air pockets in your cake, little bubbles, and if you have a really airy cake, it means all these different gases were produced that you didn't necessarily start with at the beginning. So that is a chemical change. Okay, and so last type of question here, is this a chemical change? Again, you should focus on the letters before the arrow. So here's the arrows. Look at the before and look at the after. Again, these little G's, that means gas. So is this a chemical change? And hopefully you all said yes, because you're starting and ending with different compounds. So here we're starting with H2 and O2. Okay, so we're starting with H2 and we're starting with O2, but we're ending with H2O. So a water molecule, even though it's made up of H2 and O2, it's a completely different molecule. So here's H2, here's O2, and now you're left with H2O. Completely different things. It's the same pieces, just took apart and rearranged. That's what the law of conservation of mass was saying. But we're starting and ending with completely different things. Okay. So let's kind of finish up this unit with separating mixtures. So again, mixtures can be separated using both chemical and physical properties. So if we're making a mixture, remember, we can kind of physically remove these. So we can use filtration, magnets, distillation, chromatography, evaporation, and dissolving. So these are the things we're going to be talking about now. So filtration separates mixtures by size. So if you've ever used a funnel, if you've ever made pasta, which I'll show you on the next slide, it separates by size. So here's a mixture of water and sand. Now if you pour water and the sand mixture through the filter paper, water is able to come through, but the sand is too big to fit through the filter paper. So it just kind of, chills up there and stays. So you have the sand here and the water on the bottom. Like if you've ever made pasta, that's how that works. You pour your pasta through a colander, the water passes through the holes, the pasta is too big to fit through the little holes, so it stays on top. And the same thing here, if you're sifting through different mulch or leaves and stuff, all the smaller things, smaller pebbles will fall through the holes and the bigger things will stay behind. So distillation is the separation technique that separates liquids based on boiling point. Now that's really the most important thing you need to know about distillation, but it makes sense if we take kind of like a step back and go through how this works. So you'll have two liquids, but each of them will have different boiling points. So let's say we have ethanol and water. So ethanol has a boiling point of 74 degrees, and water has a boiling point of 100 degrees Celsius. So they're in this round bottom flask over a heat source or a Bunsen burner, and it gets to a point where inside the liquid is 74.4 degrees Celsius. So at that point, the ethanol becomes warm enough to boil, and so it changes from a liquid, ethanol, to vapor ethanol, a gas. So these vapors, because it's a closed system, have nowhere to go except follow the glassware in that direction. Now, when it goes through this tube, it passes through something called a condenser. So condensation is the phase change from gas to liquid. So these ethanol vapors pass through the condenser, and in that condenser you have this cold water kind of running through it. So the gas particles, the gas vapor, kind of cools down and condenses back into liquid. So the liquid form of the ethanol is then collected in a separate container, and what's left behind is water. Now, water is left behind because the temperature inside this round bottom flask never got to water's boiling point, so it only stayed in its liquid form. So, this point right here, the liquid with the lower boiling point boils off first, and that's where that comes into play. Okay, chromatography separates dye based on molecular polarity. Now, molecular polarity we haven't talked about yet. We'll spend a decent amount of time on it when we get to our bonding unit, but molecules can either be polar or nonpolar, and that just means different ends have different charges. Again, don't worry about that. But as long as you know chromatography separates based on that property, That's all you really need to know as of right now. So you've done this in living environment. You put a little piece of dye on a piece of filter paper, stick it in some kind of solvent, and as the water goes up through the paper, it actually spreads out all the components in that dye. So then you're able to see what is in that thing. So if you were to do this with ink from a pen or a black marker, you can actually see the different colors that are in there that you don't normally see without separating it. Evaporation and dissolving. So if you had a mixture of salt and sand, and you had to separate it, what would you do? Would you sit there and literally pick out salt and sand crystal after crystal? Probably not. That would take forever, and it honestly probably wouldn't even be that accurate. So after hours and hours of work, it wouldn't even be, accurate. So what you can do is that some things can dissolve and some things can't. So if you were to pour water in this, container, the salt can dissolve, the sand does not dissolve. So if something can dissolve, we call it soluble. If something can't dissolve, we call it insoluble. Okay, so with this, if we pour the water in, now we have salt dissolved in water. So we have this salt water and the sand that's on the bottom. So that kind of helps us out a little bit. So again, if we're going to continue this, we've added our water and we stirred it. So the salt will dissolve because it's soluble and the sand is left on the bottom. Now, so here's, your beaker with salt water and sand. If you pour that through a filter paper, the salt water comes down and the sand stays behind. So now the sand is separated from your mixture and now you're just left with salt water. Now you can get that salt out of the salt water. So here's your salt water. Salt water. If you leave it just kind of sitting on the table, the water will evaporate, leaving just the salt behind because the water evaporated. And that's it. So knowing how to separate this is a huge task. Okay, so just about done. I'll just wrap up with a few questions. So what separation technique would you use to separate the drinking water from the muddy water? So let's just assume that you've waited till we've gotten to here, so everything has settled to the bottom. How could you get this out of the water? Which of the following techniques would you use? Okay, so if you chose filtration, that is awesome because all this mud and rock stuff would not fit through the filter. Okay, next question. What separation technique would you use to separate gasoline from crude oil? And again, if you said distillation, that would be perfect. Okay, what separation technique would you use to separate leaves from a swimming pool? If you said filter, that's correct because the leaves are too big to fit through the filter and the water can fit. If you also use like a little net, so there's, your net, the leaves will get stuck, the water will pass behind. Again, that is a type of filter. Okay, separating sugar from sugar water. How would you separate that? If you said evaporation, that is correct because the sugar will kind of sit on the bottom. All the water will evaporate into the air eventually. If you wanted to speed this up, you could put it on a hot plate and boil the water off quickly, or you could just let it take its time naturally. Either way, only the sugar will remain on the bottom. And lastly, what technique would you use to determine whether or not the coloring, so we're talking in food dye, is made up of a single substance or a mixture of a bunch of different colored substances. So how do you separate dyes? If you said chromatography, that is correct. Great job. So that is it. This is the last video for Unit A. There may be additional practice videos posted later on. This is the last video of new stuff. The next actual lesson video will start Unit 1, the atom. That's it. Goodbye.